Okay, so we are continuing with the calculation. Now the second stage starting from the circulator. So the main problem it comes from mixer. So for mixer T value is given, that is the temperature ratio 1.5. So now then the temperature output noise temperature under operating condition for an input temperature T naught, it's given Tn equal to 1.5 multiplied by 290. So it comes 435 Kelvin. Now this with this 435 Kelvin, we have to also consider the effect of conversion loss. Conversion loss is given as minus 5 dB. So minus 5 dB, let's take the ratio. So you have to divide it by 10. We are considering all power gain. So minus 0.5, then you take 10 to the power. So TE then it becomes 435 divided by this factor, power gain 0.316 minus the reference value 290. So it is equal to 1086. So you see, I have calculated the gain of different components of this receiver chain. For example, for the first component, which is giving 1 dB insertion loss, gain value is 0.79. What we did? Simply 10 to the power 0.1. Next we have LNA, for which in the first slide gain is given 20 dB, noise figure is given as 4 dB. So corresponding gain is 100, and noise factor from log to fraction if we convert, it's 2.51. Again 1 dB, it's 0.79 and 1.22. So how we are calculating F, this is equal to 1 plus TE by 290. Next we have the mixer. For mixer also we calculated TE 1086. Again we have the next register. So you see the 1 dB loss, it's providing different noise temperature. Why? Because their physical temperatures are different. For the first one it's 180 Kelvin, second one 250 Kelvin, and the third one 400 Kelvin. And simply we are using these two formula, TE equal to T physical into L minus 1 and noise factor F equal to 1 plus TE by 290. So that's how you can calculate these values for all these components. Now once we have all these values, then either one noise factor equation, phase equation, or temperature TE, any one of them can be used. For example, in this calculation we are considering the phase equation for noise equivalent noise temperature of the receiver. So if we go back, so equivalent noise temperature TE, this is equal to TE1 plus TE2 by GA1 plus TE3 by GA1 GA2, and it continues like this. And if we use noise factor approach, in that case F, that is equal to, this is equivalent F, F1 plus F2 minus 1 by GA1. For the next component it would be F3 minus 1 by GA1 into GA2, and it continues like that. So using then equivalent noise temperature approach, we just put the values. The first element it's giving 47 plus 438 divided by GA1, which is 0.79, and you continue. So equivalent noise temperature, it comes 640 Kelvin. So TE is 640 Kelvin. Then T operating, this is TE plus TS. TS already we calculated here, source temperature. This is 248 Kelvin. So simply add them up, it comes 888 Kelvin. This is the equivalent operating noise temperature of the receiver. If you look at here, you see the main contribution, it comes from the first component and the second noisy component is mixer. Next, noise factor approach. So, we have the values, simply put the values in equation, and then equivalent noise factor, it comes 3.21. From this, if I calculate T e using that previous formula, f minus 1 into T naught, it is equal to 640 Kelvin. So, f operating 1 plus T e by T s. So, put T e equal to 640 and T s we calculated 248, so it comes 3.58. So, f system for the given temperatures, f minus 1 plus T s by T naught, it comes 3.06. We have different forms of radar equations, some of them already we derived. If we put the values, the noise contribution, it comes K T operating minus 199.1 dB. For the second formula, again it comes minus 199.1, for the third one also same. So, all these equations you can verify individually by using their definition. In all the cases, it is coming the same value, it should be. Now, one application example, passive imaging. So, what is the difference between passive imaging and active imaging? For imaging application, we have to use some source. So, consider simply imaging at visible wavelength using any video camera. So, if we during daytime we have sunlight, it is illuminated by sun ray, but at night we have to use some source, right, of visible wavelength. Similarly, at millimeter wave frequencies also, if I want to capture image or maybe video, we need to illuminate the object first. So, if we use some transmitter, some millimeter wave source, and let us say after that one antenna, it is being used for illumination. So, we call it active imaging, where we use some source. But noting down that we can also utilize the information due to brightness, where we do not use any power source, millimeter wave source, we use simply whatever radiation already available in nature, we call it passive imaging. Then what are the different sources for illumination in this case? So, let me show you this picture. We have dwelling radiation due to atmosphere, because atmospheric particle they behave as secondary radiator, and this radiation is coming from all the direction. Let us see, we are going to image one runway without using any millimeter wave source. We are using whatever power already available in nature. So, this dwelling radiation, it will be reflected by the object. Here it is a runway, and some of this obviously this reflection, it will be in all direction, and some of this will be collected by the receiving antenna here. After some attenuation, because it is propagating through atmosphere, and how much power is being reflected by this object, it depends on the reflectivity of the surface, which is given by rho. Now, in addition to that, we have black body radiation. So, this black body radiation is due to its temperature profile. So, if temperature increases, high frequency component increases. So, for example, let me show you here. If we plot the spectral radiance per unit wavelength versus wavelength for two different temperatures, one black body, its temperature, let us say 6000 Kelvin, then this is the curve. So it peaks its in visible wavelength, and the peak appears at yellow line. If we keep on increasing the frequency for this black body, radiation decreases. Now let us consider a second scenario where the black body temperature is 300 Kelvin, quite low. In this case, peak it appears in infrared frequency range, and if you look at millimeter wave frequency band, you see we still have some radiation, even though if I compare the values, maybe it's 10 to the power 6 to 7 times lower than what available at infrared frequency. So here millimeter wave, it starts from 30 gigahertz to 300 gigahertz. After that we are calling it sub millimeter, or sometimes we can call terahertz frequency range. So at terahertz frequency, we see the contribution is more for this temperature 300 Kelvin than compared to what available at millimeter wave frequencies. So now looking at this object which is runaway and immediately surrounded by some other ground objects, so the emission, it depends on its temperature as well as the dielectric constituents of this material. So it's the property of the material. So for example, if it's very close to black body, for black body emissivity is 1, but if we take something else which is not a pure black body, which is not a very good absorber as well as a very good emitter, in that case the total emission will be much less. In previous example, we considered emissivity is 0.9 for example, then the effective temperature it becomes 0.9 multiplied by the physical temperature. So lower is the emissivity, lower will be radiation from the object. So we have a chart actually. For metal, emissivity is very small. Whatever power falls on metal, it simply reflects. So reflectivity is very high for metal, but emissivity is very small. Now if we consider hard packed dirt or any gravel surface, or let us say a muddy surface, for that emissivity is very high, almost close to 1. It is not a very good reflector, or almost it behaves like a black body with emissivity nearly equal to 1. So we have a chart here I am showing. So you see for bare metal, so these are the measured effective emissivity. Now again emissivity, it not only depends on the type of material, it also depends on the surface roughness, where you are placing the antenna. If you place your antenna immediately above that material, obviously it will receive maximum power. If you go to horizon, this power emitted from this material, it will decrease. It depends on incident angle. So we are considering the maximum case when the antenna is receiving maximum power and it's just above that material in right polarization. So this chart, it shows the variation of effective emissivity at different frequency. For bare metal at 44 gigahertz 0.01, so almost it behaves as a very good reflector. It does not emit much energy. At 140 it increases to 0.06, even then it is quite low. Now for painted metal, it is little higher. We have also painted metal under canvas, painted metal under camouflage, dry gravel, dry asphalt, dry concrete, smooth water, and rough or hard packed dirt. So you see hard packed dirt emissivity is 1 at all the frequencies. So it behaves almost like a perfect black body, and if any power falls on it, we don't have any reflection. Almost all of this power will be absorbed by it and it will re-emit all this power. So now going back to the previous one. So whatever power is being collected by this antenna, it then depends on the physical temperature of the surface, emissivity of the surface, and also the reflectivity, because it is also reflecting some of this dwelling down radiation. Now, practically in practice, this radiation due to this cold sky is very small. So, mainly the contribution due to the emission or emissivity is higher. Now, we can scan this object, and thus we can form a two-dimensional image, and since we are not using any source, so it is a passive imaging, example of passive imaging. Now, why millimeter wave? Already millimeter wave components are very expensive. Already we have this type of imaging system available at visible light, even at infrared frequency. Then what is the need of millimeter wave imaging? So, main thing, millimeter wave imaging, it can be used even under heavy foggy condition, under sunstorm, dust storm, even under heavy rain. This is the main advantage. So, we can design all weather system, even though resolution of millimeter wave image is much lower compared to infrared or visible light image. So, when visibility is very low and weather condition is bad, we can't use any other system, even then millimeter wave system will work. So, that is why it became so popular. So, now let me give one example, the significance of millimeter wave imaging. Again, going back to that plot, you see this is the radiation coming from black body at 6000 Kelvin or 300 Kelvin, this for these two different graphs. This is, for this we did not consider any atmospheric attenuation. Now, let us consider this radiation, whatever receiving by antenna, it is obviously going through atmosphere, we have some atmospheric loss. So, we are considering the effect of 1 kilometer fog. Now, the visibility in foggy condition, it varies with water content. So, here we are considering a foggy condition where visibility is 50 meter. In naked eye, you can see at least 50 meter distance. So, it an example of light fog, not even dense fog. So, in that case, if I look at the spectrum, you see it has been redrawn under foggy condition. So, millimeter wave part, it is attenuated, how much? Maybe 10 to 20 times. But if I look at sub-millimeter wave or infrared range, we have nothing, even till 10 to the power minus 10. So, infrared or sub-millimeter wave, we can say that it is attenuated more than 10 to the power 10 times, whereas at millimeter wave frequencies almost it is unaffected. That is true also at microwave frequencies, but at microwave frequencies already radiation value is smaller. So, it shows the significance of millimeter wave imaging. So, that is why we call it all weather imaging system. So, now when we go for actual design, we can't use any arbitrary frequency range. We have some atmospheric windows, we have to use those frequency band only. So, why? Let us say 60 gigahertz band. So, oxygen molecules it resonates at 60 gigahertz band and it will re-radiate, or the brightness is already very high. So, we will not have good contrast. For imaging, we need also good contrast. So, we have a effective brightness variation versus frequency. So, this curve, it shows the calculated brightness temperature of the atmosphere for T naught equal to 293 Kelvin, and when water content in atmosphere 0.1 gram per meter cube. So, one curve for clear condition and the second curve black dotted cloudy condition. For cloud is defined as 10 gram per cubic meter. So, you see the brightness, effective brightness temperature, it is quite high at 60 gigahertz due to oxygen resonance, and left hand side we have a small attenuation band due to 22 gigahertz. Similarly, again 118, 100. So we have in between some windows are available where we can use this radiometer for imaging purpose or passive imaging. So these windows are 30 to 50 gigahertz band, 70 to 100 gigahertz band, and 130 to 150 gigahertz band. Now, effective radiometric temperature. So when we are forming any image, then the received power, it is expressed in terms of some effective noise temperature T. Now, if the effective received power it varies, accordingly effective noise temperature will vary. So we can form a two-dimensional image, and for good contrast, that temperature sensitivity is also very important. So when we calculate radiometric temperature TE, we have two contribution we have seen. One, that is due to reflection, and the second one, that is due to emission. So TS plus TSC. So where TS, this is we call due to the surface brightness temperature, that is equal to physical temperature multiplied by emissivity epsilon. So it represents due to emission, and the scattered radiometric temperature TSC, this is due to reflection, that is equal to reflectivity rho multiplied by radiometric temperature T illuminator. So this T illuminator, it depends on weather condition. Under a clear open sky, T illuminator will be something, but in under cloudy condition, T illuminator will be something else. Then the effective radiometric temperature TE, that is equal to, if we put the values, it comes epsilon T physical plus rho T illumination. So it depends on the physical temperature, emissivity of that object, reflectivity of the object, and T illumination. So if I compare the contribution, left hand side, the first component epsilon T physical contribution is much more compared to the second one, but in practical system actually we need to calibrate the system first, then only we go for imaging. So this is one imaging scheme. Left hand side, it shows object, it simply follows the principle whatever we use for video camera at optical frequency range. So we have to use some focusing arrangement. So this object, it's radiating millimeter wave radiation in all the direction. So we are collecting some of them by using a focusing lens. It can be one dielectric lens antenna or simply a parabolic reflector antenna. So the whole parabola, it will collect the power, and then for a parabolic reflector at the feeder horn point, we have to place one detector array. It can be one array antennas, and each antennas, let us say, connected to diode detector, or we can use also one single antenna element. So in that case, we have to introduce some sort of scanning. So in this example, we are considering detector array. It can be an MMIC. It can be actually fabricated, and already people are using it. Millimeter wave integrated chip, where antenna, it is immediately followed by detector. So if we want, so each and every antenna, it will give you 1 pixel. If you want to improve resolution, you have to improve pixel density or number of antennas in the array. So next, it's followed by signal processing and then the display unit. So this is a very simplified diagram of a PMMW imaging system, and here we did not consider SNR. So what is the minimum power we need to sense? So there will be many calculations, and signal processing part is little complicated. So where are the applications? Some of them already are in use. For example, in aircraft landing and guiding system, and we can use them at low visibility condition for low visibility navigation, both in let us say harbor or for ground navigation as well, for reconnaissance and surveillance application, for security applications. So, for security applications, how we can use it? So, you see, millimeter wave signal, it can easily penetrate through cloth, thin clothes or even sweater jackets, but it will be reflected by skin. Now, a skin, it appears to be one warm object, that means it will its emissivity is high. Now, if we place a metal on skin, that will block that radiation from skin, and metal usually appears as a cold surface. If any if we do not have any external source which is illuminating that metal, then metal, it appears to be a cold surface, because its emissivity is very low. Now, if we use a millimeter wave source in addition to this, in that case it becomes just opposite. So, metal, it will it looks like a warm object. Now, depending on you are using active or passive imaging, obviously the image, it looks completely different, but the good thing is that millimeter wave signal, since it can penetrate through clothes, you can see concealed weapons, you can so for security applications it can be used. So, next we will take a break. After that we will discuss on transceiver architectures.